Now we will see how to carry out mesh analysis when we have a current controlled current source. Okay. Again, the circuit I have taken is similar to what I had before, and earlier I had shown you how to carry out the analysis when I had an independent current source in this branch. Now instead of an independent current source, I have a current controlled current source of value k times Ix, where Ix is the current in R13. Okay. Now as you can guess, this is analogous to nodal analysis with a voltage controlled voltage source. Okay. Now because we have studied nodal analysis extensively, by making these analogies you can see the correspondence as well as reinforce your knowledge of both mesh analysis and nodal analysis. Okay. Now what is the problem with having a current source, whether it's independent or controlled? You don't know what the voltage across that is. When we write the equation around this mesh, we don't know what this voltage is. Without introducing an auxiliary variable for the voltage drop across the current source, it is not possible to write KVL around this. So as with the independent current source, we form a super mesh, okay, which consists of all the meshes which share this current controlled current source. Okay, and then we write the equation for the super mesh. Now what do we have there? We have to take the voltage drops here, R11, R13, R23, R22, and equate that to the total voltage rise in the loop. So I'll have I1 times R11 plus R13. So if you look at it, I1 is flowing through R11 and R13, and I'll have plus I2 times R23 plus R22. I2 is flowing through R22 plus R23. Okay, the actual current through R23 is I2 minus I3. What I am pointing out is that I2 flows through R23. There is an additional mesh current in the other direction through R23 as well. And I3 goes through R23 and R13 in the opposite direction. So we'll have minus I3 times R13 plus R23. And this whole thing equals the voltage rise, which is V1 minus V2. Okay, so this is the equation for the super mesh. And the third mesh is not affected by this. So for mesh number 3, we have the same equation that we had before. This equals 0. Now the current controlled current source itself introduces another constraint. We know that the current in this minus the current in that equals this current. Okay, so by combining I1 and I2 in this branch, we know that this current k times Ix is I1 minus I2. So I1 minus I2 is k times Ix, and Ix itself is the current through this branch R13, so it is k times I1 minus I3. So if I take all the unknowns on the left side, I will get the equation for the current controlled current source, which is that I1 times 1 minus k minus I2 plus k times I3 equals 0. Okay, so this is what I'll have, and I can of course write that in matrix form. So the first row is for the super mesh, the second row is for mesh number 3, the third row is the constraint coming from the current control current source. Okay, and I will continue to call this R or resistance matrix, but you realize that this has both resistances and dimensionless constants. Okay, so these entries are all resistances and these entries are dimensionless constants. Okay, so as I mentioned earlier, this is analogous to the case of nodal analysis with a voltage controlled voltage source. So please go back and look at that case and understand the similarities between these two. Okay.